If aircraft crash investigators are agreed on measures to improve survival rates, why has nothing been done to implement these recommendations? BBC Two joins Short Circuit in the inquiry.
Every new model of car is tested again and again to make sure it will protect passengers in a crash. But the cost of crash testing aircraft is so high that only a few have ever been tested. So how do we know we're being given the best chance of survival? Plane crashes are very rare, and often little evidence survives to tell us how well passengers were protected. So investigators have to rely on simulations, using test dummies.
This is a state-of-the-art crash test dummy. It weighs just over 12 stone, and it's designed to simulate the average adult male. It's a fully instrumented dummy, and if we look here in the head, you can see that the space in the head to take accelerometers to measure head acceleration. There's an instrument here for measuring the forces between the head and the neck. And there is a neck here, which is designed to bend and behave in a way that's very similar to the human neck on impact. If we look at the rest of the dummy, you can see that it's constructed with a chest that is designed with ribs and is designed to behave in a way like a human chest during an impact. It's got instrumentation down here in the pelvis to measure the loads in the spine. And similarly, it's got instrumentation down here in the upper leg to measure the bending loads in the femur. And it's got instrumentation here in the lower leg to measure loads in the shin bone and in the knee.
It's important to realise that there are all sorts of people involved in crashes, which is why during our testing we need dummies of all sorts of shapes and sizes, ranging from a 9-month-old child through to a 16-stone man, and this dummy does weigh 16 stone. Each dummy behaves exactly as a human being would in a crash. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
This high-speed film shows how the dummy reacts to a simple impact. But real aircraft crashes are much more complicated. In 1989, a Boeing 737 crashed just yards from the runway at Kegworth. The disaster provided investigators with more information than from any other aircraft crash, from the speed of the aircraft to how long it took to stop. Large sections of the aircraft remained intact, and there were survivors.
About 8 seconds before impact, the pilot came on the intercom. He said, passengers, prepare for crash landing, very urgently. I had a picture in my mind of the safety, from the safety brochure of the crash landing position. And I recalled that I had to get the seat down in front of me. And so I punched the seat down in front of me very hard. And then I tried to get my wife's seat down. And I kept hitting it, but I couldn't get it down. And I was just returning into this position here when we impacted. Many of the seats had come off their mountings. I recall that many of the seats from behind had actually come flying up to the front of the plane with the passengers in them. There were seats upside down, there were seats under the floor, there were seats in the ceiling, it was just utter mayhem inside that cabin.
Even though the plane was only doing around 100 miles per hour when it crashed, most of the passengers died. Those who survived were all severely injured.
My injuries were that I broke both arms, I broke both my legs at the ankles, and I fractured my back in 2 places.
Most people at Kegworth died because they hit the seat in front with their heads as they swung forward. Their arms swung forward and hit the back of the seat, and their legs swung also, and they hit the bottoms of the seat. And so you've got broken legs, such as you see in this X-ray picture here. As they were swinging forwards over their lap belts, their abdominal organs were squashed, and so were their chest organs when the chest hit the knees.
Most of those who survived had crouched forward in a brace position, with their heads against the seat in front. Instead of striking the seat in front, their heads slid down the seat back, reducing injury.
Restraint in a passenger aircraft seat is by a lap belt only. And that's the situation that we had in motor cars 25 or 30 years ago. Since then in cars, we've added a shoulder part to the harness to restrain the upper part of the body. But that hasn't happened in airline seats.
Providing passengers with a shoulder strap would dramatically reduce head injuries and increase survival rates. So why aren't they provided?
Giving a three-point harness for the passenger is not as easy as you might think. We can't fix the top shoulder harness onto the wall. In a wide-bodied aircraft, we have up to 6 seats in one row. Therefore, we have to fix this top shoulder harness onto the top of the seat back. We have to therefore ensure the seat back itself is much stronger and also that it won't move forward. Conventionally, we fix passengers into their seats using a lap strap. The distance of this lap strap down to the floor is not long, and therefore there isn't a very large leverage. The force on the floor is not too strong. If we're now going to put a harness up at the top, we've got a much greater distance down onto the floor, a much greater lever, a greater force exerted on the floor itself, and there's a chance that that seat could rip out.
We could, however, change the strength of the floor. We could make an increase in the floor toughness. But were we to do that, there is actually a better thing that we can do, and that is to turn the whole of the seat around. Now, during a crash, instead of just taking the loads on the occupant just under the area of the 2 lap straps and the shoulder harness, the loads on the occupant can be taken across the whole of the area of the seat back. And the effect of that is to make it altogether more impact-friendly and to reduce the number of injuries that the passenger would receive.
If we consider rearward-facing seats, it's not as simple as you might think. We can't just take forward seats and turn them around. We in fact have to make these seats much stronger so the backs don't break forward. And the passenger sits upright, and therefore the centre of gravity of the passenger is higher. This puts a much greater load on the seat, and this load is transmitted down onto the floor. Therefore, the floor has to be stronger.
The Kegworth investigation lasted many months, and many improvements in general safety have been made. But for the individual passenger at the moment of impact, their only protection continues to be a lap strap and the brace position.
Let's put everything into context. The UK passenger carrying operation is one of the safest in the world. Thankfully, we don't have many accidents. But when they do happen, we have to analyse what's happened and take whatever course of action is necessary to avoid a repetition, and learn from the lessons to ensure that passengers are carried as safe as possible. Now that means we have to spend money, and we have to be very careful how we spend money. You can't just throw money after a problem, you have to find the right solution. And the other problem for us is that if we require our industry to spend too much money, their operation becomes too costly. The price of the ticket goes up, and that's really the rub. The passenger may well therefore be forced to buy a ticket with a cheaper operator, and that operator might not be a UK operator who's spent all the money to make that trip safer.
The Civil Aviation Authority have 2 tasks to carry out, and they are at odds with each other. The first is they've got to promote the airlines and be responsible for the cheap flights, and the second is they've got to look after safety. Now, you can't get that balancing act right if you're funded by the airlines themselves, And yet if they get it wrong, it's very difficult to challenge them because the discretion is so wide. So you've got to divide up the functions. You've got to put safety in the hands of an independent, accountable body.
Safety costs, that's true, but ignoring safety costs, I feel so much more, and it's not just pounds lost, or it's people's lives that have been destroyed, and who are fatalities or who are severely injured in an accident. And for instance, to expect people to fly with something as inadequate as this waist belt restraint is quite ridiculous. It's totally inadequate. In an airplane accident, you'll be coming in at something like 100 miles per hour, and this is all you've got to stop you in that situation. It's clearly ludicrous.
Fire is a major killer in aircraft crashes. This plane, like all passenger aircraft, was designed to be evacuated within 1.5 minutes. And yet, with 2 minutes before the flames reached the cabin, 55 passengers failed to get out and died. The Civil Aviation Authority set up a series of reconstructions to find out exactly what happened.
What was so immediately striking was the fact that although some people near the exits had obviously been able to get out quickly as soon as they became operational, there were other people from the rear of the plane who'd somehow managed to pass others who did not survive and to get out through the exits. And if you start to think about it and put yourself in that situation, if you're in a confined space, if you see a fire at one end, you make for whichever escape door you think you can get out of most quickly.
Some passengers from the middle of the fire were strong enough to fight their way through the whole length of the plane, while many around them died. Tragically, other passengers sitting by the overwing exit failed to escape. It was thought that increasing the space between the rows of seats next to the overwing exit would improve the rate of evacuation. With everything else kept constant, the experiment was repeated with different gaps.
If we look at the findings, we can see that when we have a very narrow distance between the seat rows, it takes people quite a long time to get out and the evacuation rate is fairly slow. In some instances we did have blockages. As we increase the distances between the seat rows, we can see the evacuation starts to speed up very significantly. The surprising part of the data was if we look now onto the wider gaps between the seat rows, we can see that, for instance, when we have the equivalent to removing a whole row of seats adjacent to the exit, the rate slows down. And I think what has happened is that we've created quite a large gap such that a lot of people can rush in and fill that gap, and then one tends to get congestion actually when people are passing through the exit. So the learning here is that actually in this situation there's an optimum distance between the seat rows, and that we effectively want to funnel people towards what is actually quite a small exit.
The Civil Aviation Authority has acted on the results of the experiments, and today planes have the safer seat spacing. Most of the 55 passengers who died at Manchester were killed by toxic fumes before the fire entered the cabin. Had they been given smoke hoods to protect them from the fumes, more might have survived.
Now, the first essential of a smoke hood is that it shall not burn. And secondly, since it's made of a plastic-type material, it mustn't shrink onto the wearer's head when it passes through the flame. Now, you'll see this hood here hot, but not burning.
In a smoke-filled environment, the hood must be easy to put on, and it must not restrict visibility. It must effectively filter out poisonous fumes, but let the remaining clean air in, so the wearer can still breathe.
In an aircraft fire, such as what occurred in Manchester, smoke rapidly fills the cabin so that you can't see and you can't breathe. The visible smoke is made of small particles of ash and burnt material which drift in the air.
Smoke can be collected in a chamber. Through a microscope, particles of carbon can be seen glinting in the light. If breathed in, hot smoke particles are highly dangerous.
Now we can draw those out. And here in this chamber we're doing that by a fan pulling the air through filters. The filters comprise of this paper material here, which takes out all the visible particulate matter. But what we're left with now are the invisible gases, which are the highly toxic ones, such as hydrogen cyanide and carbon monoxide. In the second layer in the filter, you will see charcoal. The charcoal is like a sponge with minute holes in it, and the toxic gases are absorbed by the charcoal. However, the carbon monoxide cannot be absorbed by that, and we have to put a third layer in, which is a catalytic converter. And this catalytic converter acts in a chemical way and converts the carbon monoxide to carbon dioxide.
Carbon monoxide is a colourless gas which burns with a blue flame. It is extremely poisonous. Carbon dioxide is far less toxic and can be detected because it turns lime water milky. Carbon monoxide has no effect on lime water. Oxygen is needed to convert carbon monoxide to carbon dioxide. Unfortunately for the smoke hood designer, if oxygen and carbon monoxide are simply mixed, they do not combine, and carbon dioxide is not produced. The lime water does not change. If the two gases are passed over a catalyst, a reaction occurs and the gases combine to form carbon dioxide. The lime water turns milky.
That, however, creates another problem. It produces a very enormous amount of heat, and it changes the inhaled air, which is now being cleaned, to a temperature in excess of the boiling point of water. So we now have to put in the base of the filter a cooler to cool the air down to a temperature which you can safely breathe.
The fitting of smoke hoods does appear to be an easy solution, but it is not the right answer. In an aircraft emergency on the ground, the important thing is to get the passengers out of that aircraft as soon as possible. If smoke hoods were provided, passengers would have to don those smoke hoods before they commence the evacuation. From our analysis, that delay in evacuation will cost lives. At the present time, we believe that providing smoke hoods in an aircraft will cause more deaths than it will save.
In the Manchester air crash, the vast majority of those victims lost their lives, not to do with the burns or the fire, but because they inhaled this thick, toxic smoke. And smoke hoods could have saved the majority of those lives. And this is something that can be brought in now relatively cheaply. You don't have to make any changes to the aircraft at all, and you can start saving lives now.
Despite concerns over safety in the event of a crash, you are very unlikely to be involved in an accident when flying. Statistically, you are at greater risk crossing the road.